start on time. Today's lecture is pretty dense, and it's a very important lecture, not only for this course, but also for later chemistry, right? So we're going to cover a lot of ground today. And I think it's something that's very important in terms of building on later chemistry courses, understanding how molecules are built up and what their shapes are and how you can predict them. So that's what we're going to cover today. It's called VSEPR theory. But we're going to cover some other things as well, like polarity and atomic structure. So basically, just to draw your attention to the fact today's lecture is based on these chapters in Silverberg. So you see we're covering really a lot of ground. There's some additional information in those chapters that we will not cover today, some background information, which is not that important. So the contents of this lecture is what's important, but these chapters here will sort of fill in the details if you're interested, okay? So, I mean, you should look at that. So I'd like to start off with some learning objectives. I posted these yesterday on Elium. These are important outcomes for today's class, right? And I guess for this week. So the first thing is to be able to draw the shapes of atomic orbitals. We're going to look at that, where that all comes from, which is pretty interesting. We're going to discuss something called the Altwell principle, right? We're going to look at quantum numbers, which define sort of where in an atom you find electrons and how you can define sort of the address of an electron. We're going to look at different types of bonding, Lewis structures, resonance, also called isomeric stabilization, VSEPR theory, and using very important VSEPR theory to predict the shapes of molecules. So that's sort of what's on the cards for today. I'd like to just say that some of this, the VSEPR theory, we have an additional task, the next one, to really cement your understanding of this, because this is exceptionally important that you understand this. So we're going to sort of fly over this today, but if you miss out on that, it's not a train smash, because we have a whole task devoted to it. In fact, we're going to discuss that, have the pre-discussion on that today, so it's nicely in line with the lecture. So, of course, the starting point is the periodic table. It always is. And we sort of discussed a little bit last week how this periodic table is built up, right? We can build it up in terms of atomic number, the number of protons in the nucleus of an atom. Atoms have different isotopes and so on, but basically the number, the atomic number, is a reflection of the number of protons in the nucleus. Now, in a neutral atom, the number of protons will be balanced by the number of electrons. Okay, so basically this number here not only reflects, or these big numbers at the top here, don't only reflect the number of protons in the atom, but also the number of electrons if the atom is neutral. Now the question is, how do these electrons actually exist in an atom? Right now, that's what we're going to sort of get our teeth stuck into today. What is the structure of the electrons around the atom, and how can we actually build that up? Okay, and to answer that, we use something called atomic orbitals. Right, so electrons exist around nuclei of atoms in what we call atomic orbitals. Now, the word orbital is a little bit misleading, because an orbital makes it sound like it's an orbit, like a planet around a star. And for many years, scientists thought that this was the structure of the atom, that you have a nucleus and that you have electrons whizzing around the nucleus like planets around the sun. It turns out, incorrect, right? But the name stuck. So orbitals is kind of a misleading term. We will see what they look like in a minute. But before we get to the orbitals, I would just like to say that all of this is based on something called quantum mechanics. Right, this is the realm of physics. So everything that we're discussing now is sort of around the turn of the 19th to 20th century, right? There was a lot of physics going on trying to understand the structure of the atom. That's quite recent. So in terms of understanding, in terms of actually figuring out how we put the electrons in around the atom, we can basically think of it in the following analogy. It's an analogy I like to use. If you want to send a postcard to someone, right, what do you need? Well, you need a street, you need a street number, and you need a city, and you need, let's say, a country, right? You need at least those 4 bits of data so that that postcard or that letter is going to arrive at the destination. Now, it's the same with electrons in atoms, okay? Each electron sort of has an address of where it is located in the atom. And we define that by these 4 quantum numbers here, right? There are 4 so-called quantum numbers. This is like the address of the electron in the atom. We have a principal quantum number, an orbital angular momentum quantum number, a magnetic quantum number, and a spin quantum number. These are the 4 quantum numbers. So you can think of the principal quantum number as kind of like the country. This would be kind of the city. This is the, let's say, the street, and this would be the street number, right? That's the analogy. Where is that electron in the atom? It's defined by these 4 quantum numbers. These quantum numbers have a certain number or a certain allowed values. So let's start off with the principal quantum number, okay? We define it with a symbol n, italic n, can have values from 1 up until infinity, in principle, right? 1, 2, 3, 4, 5, all the way up. Now, we're going to get our teeth stuck into what these quantum numbers actually mean, but I just want to sort of define the parameters first. The angular momentum, or the orbital angular momentum quantum number, we define with the cursive L, and that depends on the n, right? So n is the principal quantum number, it's where we are in the atom, the principal energy level. L is sort of the subshell type, can have values from 0 up until n minus 1 for each n value, right? And that we're going to discuss in a minute what that actually means. And the magnetic quantum number is sort of the number of different distinct ways that a specific L or a subshell type can be oriented in space, denoted m subscript L. And that has values from minus L to L, including 0. Okay, and the number of entries in that set will tell you how many ways that specific subshell type, defined by L, can be oriented in space. More about that in a second. And finally, the spin quantum number. So in each of these orientations, if you will, there can be 2 ways that there can essentially be 2 electrons, 1 spin up and 1 spin down. So each electron can be defined by these 4 quantum numbers, and then you sort of know exactly where in the atom that electron is located. So let's go over these quantum numbers. The principal quantum number, as I said, n, 1, 2, 3, up until infinity, it basically relates, the value of n relates to the energy and the most probable distance of the electron from the nucleus. What that basically means is it's the energy level, the principal energy level, 1, 2, 3, and so on. You can think of the nucleus and then these shells, and each shell is a principal energy level starting at 1, 2, 3, and so on. And that is reflected by n. This is sort of a depiction of that, right? This is just the overall picture, but now we're talking about n. So again, that's like using my analogy like the country, right? That's like where you are in the atom. The next quantum number is L, the angular momentum or orbital angular momentum quantum number, as is shown here. And what this basically tells you is that within each n, within each principal energy level, there is a certain number of L values allowed. And that depends on this rule here. So L can have any value within each n of 0 up until n minus 1. Okay? And this tells you what subshell type it is. Okay, so we have different types of subshell types, S, P, D, and F. These are the so-called orbitals. And they have different shapes, but this is defined by L. So let's just see how this works. So if I'm in the first energy level, n equals 1, what L value can I have? 0 only. Would 1 be a valid L value in n equals 1? No, because it would violate this rule here, right? So that's how this works. What about n equals 2? So if I'm in the second energy level, what L values can I have?
0.
No. 0 and 1. In other words, in the first energy level, I just have an S subshell. In the second energy level, I have a P and an S subshell. And in the third energy level, I would have S, P, and D. Now these subshells are the orbitals, and they have these cool shapes, which we're going to look at in a moment. And that is where the electrons reside. Okay? So this is the angular or orbital angular momentum quantum number. And by the way, SP, D, and F, this comes from spectroscopy that was done before the physics that uncovered all of this, which stands for sharp, principal, diffuse, and fundamental. So this comes from basically work that physicists did, and they noticed these spectral lines and they gave them these names. That's where you get the S, the P, the D, and the F from. Okay? Sharp, principal, diffuse, and fundamental. The magnetic quantum number, the third quantum number, sort of using our analogy, this is kind of the street, can go, now it depends on the L that we're dealing with, can go from minus L to plus L inclusive 0. Now what this tells us is the number of orientations that a specific orbital angular momentum quantum number, or translated into simple English, the number of orientations that an orbital defined by L can have. So for example, if L equals 0, what ML values can I have? Only 0. That means there's only one orientation of an S subshell in space. But if L equals 1, what ML values would I have associated with that? Minus 1, 0, and 1. So there's 3. Meaning that there's 3 p orbitals. Right? That's why we have 3 p orbitals, because of this quantum number. And what about D? So if my L value is 2, in other words, if I have a D subshell, how many what ML values could I have for that subshell type? Correct. Plus or minus 2, plus or minus 1, and 0. That means I have 5 values. It means I have 5 D orbitals. So this it gives you the number of orbitals for a specific subshell type. It's that simple, following this rule here. Now the last quantum number is the spin quantum number, and so you see now we're sort of narrowing things down. We've now defined the orbitals, and within each orbital can reside 2 electrons, 2. Spin up and spin down. Now you can think of an electron sort of as a magnet, but this is not really correct, but if you think of an electron, any rotating mass that has charge will generate a magnetic field. And as you can see depicted here, although this is not really correct, but this is a way that you can think about it, it can either have a spin up or a spin down sort of orientation in an electron, and it turns out 2 possible spin values, plus and minus a half, an electron. So those are the 2 allotted spin values for an electron, and they can reside in an orbital. We say, incidentally, that spin is quantized, right? Quantized means it can only have 2 values, right? Quantization of spin. So that's the last quantum number, plus or minus a half. So we've now got 4 quantum numbers, okay? And this is just to show you that this last quantum number, see this is 1920, in the grander scheme of things, that's not that long ago, right? I mean, 1920 is, well, less than 100 years ago, nearly 100 years ago. But what these scientists did is they basically passed gaseous silver atoms through a slit and then through a magnet, and noticed that the electrons interacted with that magnet, the electrons from the silver atom. Silver has a lot of electrons, and they were deflected by the magnetic field into 2 distinct beams, and only 2, right? That's where the spin plus and minus a half comes from, is the fact that you don't have a continuous band of electrons, but that it's quantized into 2 bands, spin up and spin down, yes.
Why is it 1.5 and not just less than 1?
Yeah, that's a good question. Well, why is it spin 1/2? Well, it turns out that the answer to that lies in some pretty difficult quantum mechanics. So if you want to get to that, you have to really understand quantum mechanics at a pretty high level. But what comes out of quantum mechanics is that the spin is plus and minus a half. I'll show you the equation in a minute. So those are the 4 quantum numbers. So let's just quickly, just to pin this down, well, but maybe before we do that, let's just look at the overall picture, right? This is now the structure of the atom. These are the energy levels. In each energy level, I have a certain number of allowed L values, in other words, subshell types. And depending on those subshell types, there can be a certain number of them, reflected by the ML value, the magnetic quantum number, which is the number of orbitals, and in each orbital I'm going to have 2 electrons. So this is the overall picture for the first 3 energy levels, right? In the first energy level, I just have an S subshell, and I only have one of them, because the L value associated with S is 0. Second energy level, I have S and P. Notice I have 3 p orbitals. And so on. In the third energy level, I have S, P, and D. 1s, 3p, and 5d. So this is actually not that complicated. I think this is sort of the overall structure of the atom. It's pretty structured. And the important thing is just to remember that that this structure comes from these 4 quantum numbers that we've been discussing. Now you'll notice that this is energy, the y-axis is a reflection of energy, and that these 3 lines are representative of the atomic orbitals. And I draw them on the same level, which means they've got the same energy. Okay, they've got the same energy. And in chemistry we've got a term for that, actually in physics as well. We say that if the energy of orbitals is the same, we say that they're degenerate. Now, degenerate, of course, has another meaning in English, an unpleasant meaning. But in physics, it means that the energies are the same. So we would say, for example, that these 3p orbitals are 3-fold degenerate. These are the d orbitals 5-fold degenerate. Now, by the way, there are mechanisms by which you can lift the degeneracy of these orbitals, especially d orbitals, but that's sort of in the realm of coordination and inorganic chemistry. Okay, but in a basic atom, they are degenerates. Now let's look at the shapes of these orbitals. Yes.
I'm sorry, I didn't understand why the T2p shell was on the same energy level as the 3 ones, because like the 3 shell is like 1 energy level higher, so I didn't understand.
So sorry, you don't understand why the 2p is in.
No, I do understand that 2p and 2s are degenerate because they are on the same level, but you circle 2p, 3p, and 3d, and I don't understand how come...
I've circled these 3 here because these are the orbitals that have multiple, these are the subshells that have multiple orbitals.
So basically just the 3s, 3p, 3d on the same level, and so...
They're not on the same level. These are all on different levels, but these 3 lines here are on the same energy level. These 3 on the same.
Yeah, that makes sense. Okay.
Right. So it's just to show that those orbitals have multiple orbitals that are degenerate, but the energy of 2p and 3p, of course, not the same.
Okay. Thank you.
Now, okay. So that's basically the overall structure. By the way, I should mention that this diagram is a little bit misleading because it turns out that in fact 2p is slightly higher in energy than 2s, 3p is slightly higher in energy than 3s, and 3d is slightly higher in energy than 3p, and so on. We're going to look at that in a minute. This is just sort of a diagram just showing things in a very schematic fashion. Now let's look at the shapes of these orbitals, okay? Now first of all, this equation at the bottom here is called the Schrödinger equation. I don't expect you to know this. This equation here is basically where this all comes from, right? It is an equation that has a radial component and an angular component, okay? And sort of the short and long of it is, if you take the Schrödinger equation, and well, this is actually not the Schrödinger equation, this is a solution to the Schrödinger equation, you get a so-called wave function, which we denote with this Greek symbol psi, okay? Now, if you take this equation, or this function, this is a function for a 2s orbital, this is the form of the function for a 1s orbital, and you square it, and you plot that in 3-dimensional space, you get an orbital. Now the way to think about an orbital is that we're now in the realm of quantum mechanics and probabilities, okay? An orbital, like I said at the beginning of the lecture, is not to be thought of as an electron whizzing around a nucleus. An orbital is a region in space where there's a probability of finding an electron. And the best way to visualize an orbital is like this. A probability distribution. So this is, if you take this wave function for a 1s orbital and you square it, and you plot that as a function from the nucleus, r, you end up with something that looks like this. This is a radial distribution, probabilistic plot of the probability of finding an electron for that orbital. This is what it looks like for a 2s orbital. This is basically sliced through it in 2 dimensions, a projection. And this is what a 3s orbital will look like. So we're taking this function, which is a solution to the Schrödinger equation, and we're plotting it as a probability plot, essentially, and that's what we get. And this is what they look like in 3 dimensions. Now, instead of drawing these dots, which is cumbersome, what we've decided to do to make our life simple is to draw it just with circles, with closed circles, or what we call boundary surfaces. Of course, this is now how we would represent a 1s orbital. This is a representation of a 2s orbital, okay? That's the point. And essentially, we do this just to make our life simple, but I think a lot of students get confused if you draw a 1s orbital like that. They think it means that the electron's whizzing around, you know, the periphery of this, the circumference of this circle, the sphere. That's not the case. It's a representation of what we have here. So the point is, it's all about probabilities, okay? Probabilities. Now this is the shapes or the forms of the 1s, 2s, and 3s orbitals. In other words, the s orbitals in the first 3 energy levels. Very interesting to note what the 3s orbital looks like. Notice it's basically got these 3 like rings, but that's all forming part of that orbital. Okay.
Sorry?
Yes.
No. It's like the 3s composed of 1s and 2s?
No.
Okay.
No. They're different orbitals.
Okay.
It's a good question. It's a good question. They're sort of all like collapsed on top of each other, right? Like a sandwich.
Okay.
But no, they're different.
Okay.
They're different because it comes from different functions. You see, that function gives that guy there. This is a completely different function which gives this guy here.